to address any um, issues about or questions about whether the study found a null effect um, due to um, non-substantial statistical power in their findings. So again, in science, replication is important. So you want to make sure you want to be confident um, about the effect of X and Y, because if you accept this as the truth, then the implications of the findings can be serious in the long run, right? So that's why we are replicating the findings, especially in, for instance, in the medical sciences, in the pharmaceutical studies. Um, One of the requirements in the pharmaceutical, in the clinical tests should be repeated replications over and over and over again. It should the findings of the drug being effective should be replicated, and the confidence should build up that there will be no doubts about it. Okay, but yeah, we have the side effects anyway. So there are doubts about it, but you need to provide evidence at least that the intended effect is effective anyway. So moving forward, what we can do here, since I'm not following any conventions other than the 0.05, although there are several debates on what to use, we'll just stick to 0.05. And then what we can do at our level, instead of joining the debate of what alpha should be used, is to um, plan our plan our sample size in our study. Again, our goal is to avoid the type 2 error, or the the one that I keep on talking about, uh, the type of error wherein um, the fire alarm, the smoke detector cannot even detect this issue. Okay, so there's already fire, but the fire alarm cannot detect it. So that's that kind of error that we're trying to avoid. Okay, so now um, we can now make use of the effect size um, that can to inform our statistical power. That to inform our planning in our study to reach a certain statistical power. Okay. So again, it is important so that we can detect the effect if it is really there, and we want to determine if we get sufficient number of participants. Okay. So I keep on mentioning the effect size. So the effect size, in the way I train my LBY stat students, I always ask them to report the effect size. So if you also notice in the materials that I provided you, I inserted there an instruction to always keep on reporting the effect size. Although, um, if you were unable to, if the researchers did not report the effect size, you can still come up with a computation of the effect size. Can still come up with the value of an effect size given the um, given the mean and standard deviation, the number of samples assigned per condition, or the t-value. You can still capture the effect size even if it is not reported. But um, in anticipation of the future researchers' needs, we are now reporting the effect size. Okay, so the effect size is the magnitude of the effect of X on Y. Okay, so when you say magnitude, we are referring to the impact. Impact is important when you think about what, for instance, in project allocations, in budget allocations on, let's say, multiple selection of projects, what you can prioritize. One is, of course, according to the agenda of the institution. But apart from that, let's say you want to go for impact. So if you're saying that you want to have impactful, let's say you're to have cost efficient kind of project, you want to determine what kind of intervention gives the most benefit to what you're intending to do. Okay. So that's how important effect size is because you can determine how much um, impact X has on Y. So the p-value, the statistical test, the inferential tests that we're conducting, wherein you found the p-value, it only tells us that there is a relationship, but the magnitude of the relationship is not interpreted on the p-value, but on the effect size. Okay. So the greater the effect size means the greater is the difference between two groups. So for instance, in t-tests, um, this exhibit A is the one we can say to have higher effect size. Okay? So if it were in graphs, so let's say you get the same measure. So the steeper the difference of the line is, then you might say that the magnitude of the effect of X on Y might be high. But again, don't be too dependent on graphs because the metric here can be modified. Okay, it can be larger or lower. So visually, it can impair your judgment to say that there is a higher magnitude or effect size. So it should always be dependent on the reported effect size. So for the T test, it's Cohen's d, but for ANOVA, it's the eta squared. Eta. Okay. So now I'm going to teach you how to conduct a priori power analysis. So for the postdoc, um, we're just go. Essentially, we're only measuring the achieved power. So this is achieved power. Okay. So remember Cohen's d. What we want to achieve is to have at least 80% statistical power, and we can influence the statistical power by bumping the sample size. Okay. So in conducting power analysis, we need to explain how we arrived with the estimated our target sample size. It can't be arbitrary, or it can't be just by the rule of thumb. Okay. Although in my previous experience, in my exposure in grad school, we were taught to use uh, rule of thumb practice, but it turns out that it's not a good practice, especially when you're dealing with um, when you're planning your data collection, your methodology. Okay, so as the term implies, an a priori analysis is done before the study takes place, and we are trying to achieve a desired power level. Okay, so I already discussed post hoc analysis. So I hope that you already installed the JPower. So let's conduct a priori analysis. Again, you need to look for the confirmatory hypothesis um, on the study that you're trying to replicate, or at least if it's not a replication, um, it's the it's a study that is closest to what you are doing, especially if you're um, hypothesize X and Y. It's very likely that previous research already attempted to establish a relationship between the two. Or if not, at least you have the closest related variable that you can try to capture. So anyway, so in this study, you can observe here that you have two independent variables. One is role and one is standard. Uh, and it's a 2 by 2 uh, factorial. This is a factorial ANOVA, wherein the two independent variables are both between subjects. Okay. So I already trained you how to determine the um, experimental design, right, per independent variable. Okay. So in this case, we are particularly interested in the interaction effect. Okay. So in this interaction effect, we have the effect size of partial eta squared of 0.11. So partial eta squared, again, it's just like the eta squared if you have one independent variable. But since you have more than one independent variables, the partial eta squared is the effect size specific to the x and y alone, okay, of this particular effect alone. Okay. So we are now filtering um, the other effect sizes with one another so that you can differentiate them accordingly. So it's a sorted out version of the effect size within that particular finding. So again, in factorial ANOVA, as you may have encountered in your lab in your statistics 2, factorial ANOVA has more than one independent variable, and we are using factorial ANOVA. It can be both between subjects or both within subjects, or it can be a combination of both. We call it as the mixed design. Okay. So now that we are able to identify our target effect size, since for example, we are looking, our main question lies in the interaction effect, okay, of these variables. Okay, so now moving here. Okay, so according to the test we conducted ANOVA, so that's under the F tests, and it's factorial between subjects with interaction. So this is ANOVA mix fixed effects, main effects, and interactions. So I choose this. Okay, and this is a priori. Effect size F, that's another form of effect size, but you can get that by computing it from based on other values. So in this case, we have the partial eta squared of, I forgot what's the partial eta squared value. It's okay. So in this okay, so let me review what we did. Okay. So I went to F10 and I choose ANOVA fixed effects, special main effects, and interactions. But you can also go through here. So I'm comparing means. So this is two independent groups. Yeah, gonna get there. That's just t-test. Should be ANOVA. Variances, two groups. Okay, nope, that's not what I want. It's this one. Main effects and interactions. So effect size F, you can get that by trying to transform the values from the effect size that we gathered from the article, and it says that the partial eta squared is 0.11. So I input here 0.11, okay, and I click calculate, and I click calculate and transfer to main window. So it goes right here, okay, and then let's assume that I'm striving for 95% power. So the numerator DF is 1. Numerator DF is 1. And the number of groups, in this case, technically we have 4 groups, right? Because we have a 2 by 2 between subjects ANOVA. So it's 4 number of groups. And I will now calculate. So it says here that I need about 108. This is 108. So I use 4 number of groups because it's an interaction effect. But if I'm looking for a main effect, perhaps I can just look at the value wherein it refers to the main effect, and then I will report 2 groups. So since I'm since I'm targeting the interaction effect, I use the four groups. So in this case, it's an example. If I use two groups, I will get a value of, I think hindi ko pala siya kinlik dito. Okay. So anyway, so in our example, it's 108. Okay. For this sample size calculation, I can go to the, let me share my screen again. I can go to discovering my application. There you go. So according to this report, I have a critical F of 3.93. Okay. So remember in your ANOVA, you are reporting the F ratio. So if the critical F means that if the F value goes beyond this level, it means that you successfully you can successfully reject the null hypothesis. So in this case, going back to the slides, in this case, the F value here is 5.17. So the F ratio here went beyond the critical ratio F. So it means that in that case, we can reject the null hypothesis. Okay, does that make sense? Can you recall your statistics course wherein you have your critical value, right? So this is your critical value. So if it went beyond the critical value, so you are now rejecting the null hypothesis. I don't know how much you can make use of the statistics tool if that simple concept does not ring a bell to you. So this is your normal curve, and you have your critical value. This is your critical value. So if your test, inferential test, for instance, the critical value is according to the one I did today, it's 3.93. Okay, so I will do that. I will show it to you here. Yikes, stop sharing. 3.93, for example. 3.93, or in this case, it's 4.06. Okay, so let's do the 4.06. Critical value 4.06. Okay. So notice here that my F value here, my F value is beyond F 4.06, right? So this is, for example, 5.17. Okay. So it means that you need to reject the null hypothesis because it went beyond the critical value. So in that case, what I'm just trying to demonstrate to you is that the findings that we get here already went beyond the critical value. That's why it got the result of rejected null hypothesis. That's the only main thesis that I'm trying to say. Okay. Okay, so vaguely and looks familiar should be okay, I guess. But that's just the main idea. Let's say if you have your basketball. So this is your basketball court. So na-shoot siya. Ganun. So na-shoot siya, critical value ito. So this is your critical value. So it went beyond the critical value na-shoot. Now you reject your null hypothesis. Okay, so now in our sample size calculation. So let's assume that I'm using, let's say, number of groups of 2. what I'm trying to demonstrate to you here is that the total sample size that we're going to get will change depending on our target power. So the higher the power that we're intending to get, the higher sample size that it will show, okay? That we will need, okay? So in this case, if we have 0.8, we need a total of at least 0.67. But let's say if I increase our target power of 0.2 to 85%, notice that the total sample size went up to 0.76 to 76. If I increase it again to statistical power of 90%, notice that the total sample size increased to have at least 88 sample. And then in this case, to 95%, to reach that power, I need to have at least 109. And if let's say I want to achieve 99% statistical power, that's my plan. I want to achieve 99% statistical power. I need to have at least 152 sample size. Okay. So here is an example report that I'm expecting to read in your laboratory report. So here goes. So a power analysis to calculate the necessary sample size was conducted using G-Power. Using the software, we entered the analysis of variance test a priori type of the power analysis. The effect size is determined to be F is equals to 35, which yielded a sample of 109 participants for 95% statistical power. To replicate, you see here, I use the main effect, right? That's why we use 2. So in that case, you need to highlight where the um main effect is. But in this case, I think they were not able to report that. That's why I used this result instead. Okay. So moving forward, hindi ba main effect tong isa? Hindi, dapat isa pa. Plan comparison pala. Okay, so that's like a post-hoc t-test. Okay. So anyway, you 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 need to report, let's say, to replicate, let's say, whatever confirmatory findings that you want to get to capture. So in this case, a main effect of standard on predicted enjoyment. So you report here the independent and dependent variable, and whether you're trying to replicate the main effect or the interaction effect. And then you cite the study and which specific study in the paper you're trying to replicate. So we plan to include 109 participants in our sample. Okay, so in my own study, so I use, for instance, from a multiple regression. I'm going to conduct a multiple regression analysis using 2 predictors while testing for difference of the variance. So I go to correlation and regression, and I choose linear multiple regression. Okay. So in my study, I'm going to use multiple regression. Okay. So in this case, I have if I enter, let's say I have f squared of 0.15, so it should be f squared pala. Okay. 0.15, I get, let's say, a total sample size of 89 respondents. Okay. So number of tested predictors, 1, number of predictors, 2. So I have, let's say, 2 predictors, but I'm intending to locate the X and Y, so that should be just 1 predictor. If I can remember it correctly, the other variable is just a control variable. That's why I used the tested predictor as well. So it depends on your model on what to put in your GPower. Okay. So in this case, for instance, we want to let's check for the achieved power, okay, in our target study. So in my study, I used a total of 117, and then the actual effect size is found to be 0.59. Okay. So technically, it's higher than what I expected. Okay, the effect size is higher than what I expected. Okay. Because remember that I have a total of 117 sample, but according to the results, if just getting a minimum of 89 sample, I will already achieve 95% statistical power. That's why in my actual study, my achieved power went so much higher. Okay. So in this case, the achieved power here is 100%. Okay. So, but there is a concept called overpowered. So especially that now we're dealing with big data. So the caveat in overpowered data is that the statistical significant findings can become trivial and might no longer be um, interesting to look at because you will find a lot of asterisks around. Let's say you have your visual representation of asterisks. Any variable that you will put into your model will be statistically significant. And in that case, it might not be interesting at all if you have overly powered data. So, but that's a problem for big data conventions when we're dealing with scraping of data online. So that's the big data conventions. Okay, so okay, let me just skip this. It's just a demonstration of how much are we getting from the it's just a graph showing the estimate number of sample size given a certain power. So according to the 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 actual study that I conducted, I can reach 95% statistical power even if I reach 25, even if I only have 25 sample size. So it means that the effect of X and Y is so strong. Um, it may be because the measurement that you use is more probably more rigorous, or maybe the model is better wherein your control factor is included in the model. That's why the effect between the X and Y is shown to be stronger. So you see, if you have really good conceptualization and if you have rigorous method, you can um, really use it out. So it can be more efficient in your research if you really uh, if it's if it really makes sense theoretically, if it is theoretically sound, and if the method is rigorous, you can really get good findings. So anyway, I'm not saying good in a way na there's value judgment of the relevance, but what I'm trying to say is that good because there is an expected effect anyway, according to how I conceptualize it. Okay. So okay, so let's stop here. Okay, I'll stop here. Okay. So in this case, we're going to find the results section. There you go. Okay. So let's try computing for the target sample size if we are to replicate this non-depletion and depletion condition. Okay. So let's try it. So here we can see that our target is 0.84. Okay. So and they conducted t-test. Is this between is it independent samples t-test or within our paired samples t-test? What do you think? Again, that's important, right? We need to know that. In this case, this is a independent samples t-test because in our exercise last week, we concluded that this is a between subjects design. Okay, so this is an independent samples t-test. Okay, so in that case, I'm going to oops. I'm going to go to t-test and choose difference between independent means, two groups. Okay, because it's independent samples t-test. Okay, I will choose one-tailed because I'm intending, okay, maybe I'll just choose two-tailed because I'm not sure what I'm trying to, what I'm expecting here. Okay, so, and then the effect size is 0.84. So it's effect size D, right? And then let's say I will try to get 90% power. So for the allocation N2 over N1, you need to determine here whether they are proportional. Let's say you get, they reported that their um, one group is 50 and the other group is 50. So the allocation is perfect one. But if you get, let's say the second group to be 60 and the other is 40, then you need to divide that to come up with the ratio. Okay. So in this case, I will just assume that they are equally proportional. So I'll just put one. Okay. And then let me calculate. Okay. According to my static power analysis, to get to achieve 90% power, I need to have at least 62 participants. Okay. So it says here that for the first, I need to have at least 31 participants per sample. Okay. So try pa natin isa pa. Sobrang useful nito guys, promise. It saved me a lot of heartaches in my studies. I always get statistically significant findings because I'm confident with the rigor in the method and the concept in my conceptualization, but I also address this issue. That's why I always get um, statistically significant findings. So this is just a method results. I need to go to results. Okay, no more examples. Let's go to Knight et al. Study 3. Knight et al. Study 3. Okay. So here is the findings. Only interaction effect was significant. Okay. Let's say that I'm interested in their interaction effect. That's my target, for example. So now I'm going to, if I want to replicate the results, I will copy, I will use the same instrument that they use. I want to plan for my next study, and therefore I want to make sure that I have substantial sample in my study. So I'm going to compute for a priori power analysis. Okay. So it says here that the semi-partial correlation is 0.078. Now I will compute for the, okay, so let's say I'm going to conduct ANOVA. This is ANOVA fixed effects, mean effects, and interactions. And I will input here 0.078. So it's right here. Let's say my target is 90% power and my numerator DF. Okay, since I'm now planning for an interaction effect, I will now put here 4 groups. Okay. So my numerator DF is still 1. Okay. I will now calculate. So it says here that I need to have at least 127 participants. So if I will increase that, let's say to 95 percent statistical power, it's now 156. Okay. So I have a question for you. So what if, let's say, what if the semi-partial correlation here, which is what we're using as the effect size, is becomes equal to 0.1? What do you think will happen to our sample size? Will it increase or will it decrease? if the effect size is higher, what do you think will happen to our target estimated sample size? Will it increase or decrease? So what will happen is that if we have higher power, okay, so let's try to put it here, 0.1. Okay, and then we'll calculate. The sample size now is decreased. Okay, so the reports are, everything that you do here is reported in the on this side. Okay, so notice here that if I have a effect size that is higher compared to the other, with the original one, our target sample size is 156. But when our effect size went higher, the total sample size decreased from 150 plus to 119. Okay. So this is a proof of concept of what the Cohen indicated before, that it affects this triad affects each other because it is designed that way. Okay, so it is designed that way. And we just need to make sense on that in terms of practical implications. That's why if you're going to look for an article that you want to replicate for the demonstration sake in our course, I want you to look for an experiment that has higher effect size. The higher, the better. So you can Google if the effect size reported there is considered medium or high. Okay, but if it has small effect size, then it will require you eventually to get a lot of sample eventually because it has small effect size. So you will need lesser number of sample because the threshold is easier to be met because of the higher or greater effect size. So it means that the fire out there is so big that everyone can detect it easily. Okay, that you don't have to get a lot of several cases in your study to be able to detect it because the impact between X and Y is so great that when we conduct analysis, it's easier to even with relatively lower sample size, we can still detect that. That's why in um, cognitive psych research topics, they usually have um, low sample size because they're looking for basic processes that are easily detectable. So the advantage now here, remember our discussion in the within subjects design wherein you have higher statistical power. If you look for experiments that are using within subjects design, you are more likely to but with also higher with high effect size, medium to large effect size, then you most probably will have an easier time in conducting your study because you will have less number of target samples to invite. So that's the practical aspect of understanding power analysis. Okay, so that's very useful. Okay,